Hi, everyone. Welcome to AKM Analytics, where we empower data driven decisions. My name is Estras Koome. Today, I'll talk about simple linear regression model in R software. Sit back and enjoy as we learn together. So, what's a simple linear regression model? A simple linear regression model is a statistical term or is a statistical method used to understand the relationship between two continuous variables. One that is independent, that is denoted by x, and one that is dependent, which is denoted by y. The model assumes that there is a linear relationship between these two variables. In other terms, we assume that there's a correlation between x and y. So, simple linear regression model can be described or can be presented by the equation y is equals to beta naught plus beta 1x plus the epsilon, where y, of course, is the dependent variable, sorry, and x is the dependent variable. Beta naught is the intercept of the regression line. What do I mean by this? Um, when the value of x is equals to 0, beta naught represents the unit change of y. It gives the unit change of y, while beta 1 is the slope of the regression line. What does this represent? This represents, given that the unit change of x is equals to 1, then it shows what is the effect of change it causes y. And of course, epsilon is the error term, which is the difference between the predicted values and the observed values. So, for instance, let's say you own a business and are curious about how many clients you'll have in future after raising public awareness. Through various campaigns, you keep track of information about public awareness campaigns and the number of clients registered. So from this scenario, we want to determine the number of clients we shall have in future with respect to the public awareness campaigns conducted. So the customers registered is our dependent variable, and the public campaigns awareness is our independent variable. So we can present this as a simple linear regression by taking number of clients registered in future um, as the y, and x to be the number of public awareness campaigns conducted. There are conditions that must be met when conducting simple linear regression. One, linearity. Correlation has to be there between x and y. Number two, independence of errors. The residue should be independent of each other. Number three, we have homoscedasticity. The residue should have constant variance at every level of x. Number four, we have normality of errors. The residue should be normally distributed. Number five, multiple linearity, which is not an effect to simple linear regression, but once we proceed to multiple linear regression, you'll notice the effect of multiple linearity. Now, to check whether these conditions have been met, we use what we call diagnostic plots. Our first diagnostic plot is the residues versus the fitted. This plot shows the residues, which are the errors, versus the fitted values. Ideally, there should be no clear pattern, a random scatter, in these plots. A slight curve here will suggest some potential nonlinearity. Our second diagnostic plot is the QQ plot. The QQ plot compares the distribution of residues to a normal distribution. The point should follow a straight line, hence suggesting that the residues are approximately normally distributed. Our third diagnostic plot is the scale location plot. This plot shows the square root of standardized residues versus the fitted values. It's used to check for homoscedasticity. A horizontal line with equal spread points is ideal, else we shall rule out heteroscedasticity. Our last and fourth diagnostic plot is the residues versus the leverage. This plot identifies influential data points, observations with high leverage. There is a Cook's distance line that indicates whether or not the points seem to be far below this line, hence suggesting if or not there is existence of any single observation which is unduly influencing the model. If nonlinearity or heteroscedasticity is a concern, you could consider transforming the variables or using a different model that better captures the relationship between x and y. You could also check on any outliers or influential points that might be affecting the results. That is the end of part 1. See you in part 2, where we shall be conducting the coding in R.